Good evening. So, today we will talk about the spin crossover, but we have started our discussion also. So, we have seen that crystal field theory predicts that some of the complexes can be in the high spin state and some more are in low spin state. So, if we try to find out the corresponding magnetic moment, we will see that in this particular case the magnetic moment would be different compared to the low spin state. Here also we can compare the magnetic moment with that of the high spin molecules. So, high spin states are characterized mostly by large number of free spins. So, the determined magnetic moment what we can determine experimentally would be high also, and in case of low spin state this would be low. So, this particular thing will interested to know where this particular crossover is taking place. It can be dependent on the crystal field splitting, and also the corresponding different nature of the ligands, that means the ligands as well as the metal ions and their oxidation states. They all play some important role and do contribute to the system where we find that at particular region, say in this particular region, we do observe the corresponding changeover from a high spin state to a low spin state as we increase the temperature. With the increase in temperature, therefore, increase in T value, we will find that the corresponding spin state will be changing from one particular position to the other, and at the same time we will be using the corresponding magnetic moment values for the characterization. So, these compounds, when we consider them as the corresponding complexes, they are also known as spin crossover complexes or SCO complexes in coordination chemistry or transition metal chemistry. So, we will just little bit we will just go through some of these techniques, because the basic reason behind the formation of these types of complexes we have discussed. So, what are the techniques basically available which can be useful to detect this particular phenomena in different transition metal complexes where we have unpaired spins. So, manipulation of the number of unpaired spins for a complex which we designate as the high spin, as well as for the complex where we can designate it as the low spin, how we can detect nicely using some of the physical techniques. And one such technique is definitely the crystal structure determination, because in crystal structure determination we find that this X-ray crystallographic data, the single crystal X-ray crystallographic data can be useful to find the corresponding bond distances between metal and the ligands. That means the ml distances we can find the corresponding bond angles as well as other metric parameters related to the corresponding metal complex. So, once we determine the metal ligand distance, it gives insight into the spin state of the complex. That means, when we find out precisely the ml values and also the LML angle from the X-ray crystallographic data, we will see that in some cases these values are high and in some cases they are low. That means, when metal ligand distances are high, definitely we have the corresponding metal center with EG electron configuration. The electrons in the EG level can give rise to longer ml bond distance, because those orbitals containing the metal ions having the EG electronic configurations are directly facing the ligands along the corresponding Cartesian axis in a octahedral geometry, say. So, the basic example what we will see that there is a corresponding electronic configuration in octahedral symmetry that this ml distance should be high. Similarly, when it is low, the ml bond distance is low, and these when we compare, so they are comparable. So, only we have the electrons in the T2G level and vacant EG level. So, the vacant EG level will contract the ml distance, and that basically gives rise to the corresponding shorter ml distance in case of the situation where we get the only electron in the T2G level. So, the electronic configuration in EG level is for the high spin complex, and this is for the low spin complex, as we all know. So, the X-ray structural data nicely explain the two situations where we can have the high spin compound as well as the low spin compound. So, we can determine the spin state here, and the interest for this type of complexes in recent years also, because the phenomena is known for say 60 to 70 years when first discovered, but the recent interest for this spin crossover phenomenon also leads to advanced technological applications such as different types of spin based switches, data storage and optical displays. So, whether these metal complexes can be useful for all these devices, the device making things have been utilized for the use of these interesting class of molecules. So, what we have just seen that we can determine not only the X-ray structure, but also we have to determine the corresponding magnetic susceptibility, and these magnetic susceptibility values can be very nicely measured in such thing where we will find in detail also when we will study the magnetic properties of all the transition metal complexes or the coordination compounds in detail. But right now we can see that this magnetic moment where we just determine the corresponding product, that being the susceptibility and the temperature product, is utilized as the principal technique to characterize the SCO complexes. So, the susceptibility what we can determine using some Gauy balance. So, homemade Gauy balances are there. That was the oldest technique where people can measure the corresponding magnetic moment values. It is nothing but the weighing of the sample there are several steps over there. We can have a very small Gauy tube which is very much similar to the tubes what we use for NMR measurements and EPR measurements. So, this Gauy tube is initially is empty. So, for empty Gauy tube we take two weights. So, it is basically a balance, a very sensitive balance, and we will be taking the weight in presence of the magnetic field and in absence of the magnetic field. So, when the field is on and the field is off. So, the empty tube in field off situation and field on situation. Then in the second step, what we can do? We can do that the corresponding tube will be packed with powdered samples. So, powdered sample of the compound is packed, and then again we will take these two, that means field off situation and field on situation. So, we will have four weights, four different weights, and from the difference of all these weights we just basically calculate the corresponding susceptibility value. So, we can calculate the corresponding gram susceptibility, then we can multiply it with the molecular weight of the compound, giving rise to corresponding molar susceptibility, and when we multiply it with the temperature of the measurement, this particular product, that means chi mt, can be used for the calculation of the corresponding magnetic moment. So, effective magnetic moment can be determined. So, one such technique is the Gauss balance technique. Then we have the susceptibility balance, little bit sophisticated compared to the Gauss balance. Then the susceptibility balance, those balances are available. Then we can have the vibrating sample magnetometer, which are also useful, and they are also useful for variable temperature measurements also. Variable temperature measurement, and the most recent one and is highly sophisticated one is the squid magnetometer, which is superconducting quantum interference device. So, this superconducting quantum interference device is the most sensitive one, which can measure nicely the very small magnetic moment values. So, very small values can be measured. Even this technique is so sensitive that we can handle the biological samples. Particularly these transition metal bearing metalloenzymes. So, these metalloenzymes, so certain of these metalloenzymes which can have at the center a paramagnetic metal ion. A paramagnetic metal ion we can have, and that can show its corresponding magnetism. So, how to detect that paramagnetism, because these metal enzymes have several thousand, say 15,000 molecular weight. So, several kilodalton molecular weight it can have. So, have high molecular weight with say 1 metal ion which is paramagnetic. So, the presence of this one metal ion within this particular huge molecule, huge biological molecule is definitely a difficult task to use as its corresponding measurement for its susceptibility. So, squid is well suited for measuring that particular magnetic moment which is available through some metalloenzymes. So, these are the different techniques what we can use for these magnetic moment measurements. So, the measurement for this magnetic susceptibility for characterization of spin crossover complexes is the most useful one, and if we just plot the chi-mt values which is centimeter square mole inverse K against temperature in Kelvin. So, from 100 to 300 Kelvin, if we plot these susceptibility and temperature product. So, the product of susceptibility, molar susceptibility and temperature, this is chi-mt. So, chi-mt against temperature. So, what we will find that at low temperature, this is the axis where the magnetic moment can increase. So, with rise in temperature, the chi-mt values are increasing. So, these are the corresponding data values at particular temperature. So, as we move from say 30 or 25 degree Kelvin, and as we move upward, so around 175 K, this value of the magnetic moment is rising very fast, and within this particular zone basically. So, it is close to 170 to 180 Kelvin. So, 170 to 180 Kelvin, the molecule is entirely transforming to a low spin state to a high spin one. So, sudden jump in magnetic moment say from a value of 1 to 3 is due to the corresponding transformation of the molecule from a low spin state to a high spin state is clearly seen from this particular plot. It is a very simple plot, we can determine even with the use of the primitive Gauss balance. The Gauss balance can be utilized for the determination of the susceptibility parameter and the temperature of the measurement, but only difficulty is that the Gauss balance cannot be operated nicely at different temperatures. So, at least we should have the corresponding vibrating sample magnetometer if the squid is not available, or any other type of magnetometer which can be utilized for measurement at different temperature values. So, these different temperature values gives us certain magnetic moment values related to the corresponding molar susceptibility at different temperatures. So, as we cross 200 degree Kelvin, and after that there is a marginal change in the corresponding magnetic moment value, that means the magnetic moment value at the high spin state has been saturated. So, we get this temperature range, basically this particular temperature range of 170 to 180 Kelvin is the typical range for the corresponding spin transition. So, this is the corresponding region where we can assume that their spin crossover is taking place between the low spin state and the high spin state. So, this is basically nothing but the magnetic susceptibility plot showing a spin transition at around 180 K. So, we have the range, that means it is starting from here and ending over here, but the average is this particular point. So, this particular staircase type of plot is well known for us for the other type of physical measurements what we find for the potentiometric titrations of acid and base and the redox parameters. So, we get this type of plot. So, at 180 K we have the corresponding transition from the low spin to the high spin, and this is a very recent work, people have done it in published in Dalton Transaction in 2005. So, the second technique after the magnetic moment and X-ray, rather the third technique will be the Mossbauer spectroscopy. The Mossbauer spectroscopy is very much useful if we have the corresponding iron compound. That means, if we have iron and whether that particular complex is in the low spin or the high spin, that can be very nicely tackled if we have the monitoring system using the Mossbauer spectrometer. So, Mossbauer spectrometer can utilized for this particular isotope of iron, that is 57 iron, which is Mossbauer sensitive, and the technique through this measurement gives the proportion of iron 2 and iron 3 centers that are high spin and low spin states, because the isomer shift and the quadruple splitting differ significantly for these spin and oxidation states. So, both these two oxidation states is a very nice technique, that iron 2 in Ls and Hs and iron 3 also in Ls and Hs can be handled. That means, if in a particular compound, if we have both iron 2 and iron 3 compound, those two oxidation center as well as the high spin and low spin proportions are present. So, we should have the corresponding signature in Mossbauer spectroscopy, that whether all 4 systems, that means iron 2 low spin or high spin and iron 3 low spin or high spin is present over there, can be found out, because in all 4 species the corresponding isomer shift and quadruple splitting, these are the 2 valuable parameters to judge a particular Mossbauer spectra. So, these values basically tells us immediately that whether the center is in high spin or the low spin state. So, therefore, this particular spectroscopy is also helpful in identifying the corresponding spin crossover or the spin state equilibrium situation. So, this is the thing where we can get, this is the overall spectrum, and these were the corresponding simulated one. That means, we have basically 1, 2, 3 spectra within this particular overall spectrum, and this is a corresponding Mossbauer spectrum of an iron compound. So, this black dotted one, and the red and blue and green lines, we can have the corresponding red, blue and greens, these 3 lines. So, we can basically simulate the entire spectrum for the individual component. So, one particular component we have, the second one, this one, and the third one also are the simulation of contributions of 3 species only, not all 4 species present. So, that means, the simulation of the entire spectrum gives us that the spectra what we are getting is basically a mixture of 3 components, and the simulations basically giving us the contributions from low spin iron 2, high spin iron 2 and low spin iron 3. One is missing, therefore, that means, in this particular case the high spin iron 3, that means high spin ferric compound is not available. So, iron compound, that particular iron complex at 300 K, which is close to room temperature, give rise to the proportions of 3 different species. That means, we cannot control the corresponding oxidation state. That means, exclusively we are unable to produce the compound in the ferrous state. It can have some ferric component, and the ferrous state again present in 2 forms, that means both low spin and high spin, but the ferric form is present only in the low spin form. And this is also another observation in recent years, which is published in Journal of American Chemical Society in 2007 by Kim Dartmouth and his group. And 2 other examples what we can see, that right now we see that the Mossbauer spectra can give rise to the corresponding environment for iron 2 and 3 in both high spin and low spin form. So, this spectroscopy is basically can be utilized to identify these 2 oxidation states in several of the compounds and if the spin state equilibrium is present, we will see that some equilibrium is operating between the high spin state and the low spin state. Similarly, for the ferric state also we can have the low spin state and high spin state, and these two states can be in equilibrium at the same time. So, the basic proposition what we were dealing with in the original assumptions for this spin crossover complexes, that one particular spin crossover complex we can have provided we choose the right metal ion and the appropriate set of ligands. These two things basically tells us that this particular metal ion in these ligand environment can have the corresponding chances to provide both high spin and low spin compounds, which is controlled by that corresponding temperature variation. So, the right metal ion, luckily when we are talking about the corresponding Mossbauer spectroscopy, we are lucky enough to take the corresponding iron center as its Mossbauer spectra. We will be talking about the 57 iron species. So, 57 iron isotope can give rise to these signatures for these two different types of splitting, for isomer shift and the corresponding quadruple splitting. So, when we measure that how far it is going from the central position, that basically tells us about the corresponding isomer shift, and one particular spectra how the corresponding signature is being splitted into a doublet or so, that will give rise to the corresponding quadruple splitting. So, we just simply take the tris phenanthroline compound. So, is a very useful compound. We will find this compound in the corresponding optical spectroscopy also. So, 3 phenanthroline ligands when attached to the iron site in the ferrous state, we get the compound like this. So, we have the octahedral center, and this octahedral center is nicely providing us the corresponding tris chelate, and it is in the ferrous state. So, 2 of these X groups, it can be chloride, it can be bromide, or it can be iodide. Depending upon the compound's isolation technique, we can have 3 different salts from there. So, is a dicationic compound is obtained as its corresponding salt, and these anions also have some profound effect due to the crystal field packing for their high spin and low spin states. Similarly, one other compound we can have where one of the ligand can be replaced by 2 thiocyanate groups, because these thiocyanate groups can give rise to a different crystal field parameter to the iron site, and that the change in this particular thing can be comparable whether that particular phenanthroline substitution, that means we are substituting one phenanthroline by 2 thiocyanate groups, and these orthophenanthroline groups are organic nitrogen bearing groups. So, these are also nitrogen donors to the iron site, and 2 of these nitrogen sites of the one phenanthroline ring is changed or is substituted by 2 thiocyanate nitrogens, which are purely inorganic in nature. So, the nature of the nitrogen environment compared to the phenanthroline can be compared when we move to the other compound, and we can have the particular type of transition at a different temperature. So, the other molecule will look like this. So, we just have not substituted these 2 groups. So, these 2 groups are still there, and we are having only the corresponding NCS and NCS binding. So, the environment around iron is still Fe(N)6. This is also Fe(N)6, but already we have seen from the spectrochemical series that the position of the thiocyanate groups are different compared to the phenanthroline, because the phenanthroline ligands are stronger compared to the thiocyanate ligands. So, we are providing some little bit weaker crystal field parameter around this particular iron again in the ferrous state. So, what basically we will see that in case of the triskelate, we have the corresponding Mossbauer parameters or the Mossbauer splitting in their corresponding spectroscopy. We find that as we move from 5 Kelvin to 300 Kelvin, we do not see that the values are changing, the relative transmission is changing, but the corresponding splitting is not changing much, it is almost same. That means, with change in temperature, we are not getting any kind of transition from 5 K to 300 K for this particular compound. So, whatever environment we can have provided by the phenanthroline ligands. So, 3 such phenanthroline ligands are providing a strong crystal field. So, a strong crystal field is being provided to iron center, and that center is therefore low spin in nature. So, the crystal field strength, that means the delta value, the delta O is basically dictating the corresponding spin state, and we are not close to the corresponding equilibrium situation or the crossover region, where we expect that with rise in temperature our spin state can change from one spin state to the other spin state, but it remains in the low spin state only. So, what about the corresponding thiocyanate species? We will find that here the expected thin is operating, that as we reduce the corresponding crystal field strength by substituting the corresponding phenanthroline. So, orthophenanthroline, one orthophenanthroline is being changed with 2 SCN minus ligands, and in the spectrochemical series we all know that SCN minus is less than orthophenanthroline in spectrochemical series. So, this will exert stronger crystal field compared to thiocyanate. So, to get this spin crossover complex, our original idea is that how we get the corresponding spin crossover complex. How to get that? So, when the ligand is strong enough, such as phenanthroline, and when we are providing 3 in that triskelate, so in case of triskelate we are providing 3 orthophenanthroline together, that means we have the corresponding stronger crystal field. So, we have the stronger crystal field, and in this stronger crystal field we have the corresponding delta octahedron which is greater than P, and we will end up with low spin situation. But when we go for the thiocyanate compound, we are compromising, that means we are trying to reduce the corresponding crystal field strength, and as we reduce the corresponding crystal field strength, our expectation should be there also with 2 substitution of this thiocyanate by 1 phenanthroline, that our delta octahedron would be comparable to P. So, that is the expected condition or expected situation where we can have the corresponding spin state equilibrium. So, once we get the spin state equilibrium for this particular situation, so once we know that definitely only the low spin compounds are forming, so we can go on reducing the corresponding strength of the corresponding crystal field such that we at one point we should have high spin compound. So, at 77 K, which is liquid nitrogen temperature, because this 5 K for this particular compound is close to liquid helium temperature, which is 4 Kelvin, and this can be measured nicely at liquid nitrogen temperature, and this liquid nitrogen temperature gives the corresponding measurement at 77 K, and we have almost two merged lines. And as we move up, we get at 180 K, the values are this particular splitting is increasing. At 184 K, we have 1, 2, 3, 4, all 4 signatures are present. Similarly, for 186 also. So, this is the range what we have seen in one other previous example, that around 185 Kelvin that corresponding transition is taking place from low spin to high spin. So, the magnetic susceptibility data what you have seen earlier in one other example, this similarly applicable for the Mossbauer spectroscopic data as well. And when we have exclusively the low spin situation, we have the splitting like this, but as we move up, we go for further splitting and the signatures for the high spin is also coming. That means at this temperature range, we have both high spin as well as low spin molecules. So, the molecules were entirely low spin at low temperature at liquid nitrogen temperature. As we rise the temperature, so some of the low spin molecules are transforming to high spin and they are in a dynamic equilibrium. That is why we are getting the signatures for the 4 lines in the Mossbauer spectra, 2 for the low spin species and 2 for the high spin species. And as we move upward and when we reach around 300 K, that means the room temperature, when we just exclusively reaching at room temperature, the corresponding the spectrum is for the corresponding ferrous iron in high spin state. So, we have the different splitting and the different separation for these 2 lines, which can be characterized for the high spin state of the molecule and which has been achieved at 300 K. So, that is why this spectroscopic data, the Mossbauer spectroscopic data are nicely explaining the corresponding data or the corresponding explanation what we get for the magnetic through the magnetic moment measurements. So, those magnetic moment measurements are not so clearly seen that which particular point we have the corresponding transitions and whether the situation is in equilibrium. But here we say that all the 4 lines and the corresponding equilibrium between the low spin and the high spin states are present in this particular temperature range. So, next we will just see another spectroscopic technique which is very much similar to the infrared stretching frequencies, which is Raman spectroscopy. So, how Raman spectroscopy can be useful for determining some of these useful compounds in the high spin and low spin state. So, whenever we have a covalent bond or the coordinate bond such as X and Y are bound together, it can be for simple molecule like carbon monoxide also. Then we will find that this particular one are fixed with this covalent bond and they are vibrating along the bond axis. So, we have 2 balls basically these balls are X and Y and they are connected through a spring which is the corresponding bond. So, corresponding stretching frequency, as we give the radiation in the IR range, the IR frequencies are useful and can be absorbed by this particular bond stretching for the atoms which are connected together. So, similar thing is also can be obtained if we have either this particular molecule serving as a ligand bound to the metal system. So, this can be a ligand which can be bound to the metal center, or there are some other cases where we can have the corresponding stretching frequency between the metal and the ligand. And Raman spectroscopy is another technique closely related to the FTIR or the infrared spectroscopy, where we can monitor the corresponding ML bond distances, where we have seen that ML bond distance are changing as we move from high spin to the low spin state, and the vibrational mode which is associated with the ML bond is definitely be affected or changed as we move from the high spin state to the low spin state. So, this particular simple assumption is useful to tackle this particular complex situation for the spin crossover complexes by using the Raman spectroscopy. So, it can therefore be used to identify the spin state, that which particular spin state is dominating in a SCO complex. So, whether at a particular temperature it is the low spin complex which is exclusively present in absence of any high spin species, or as we increase the temperature the situation is changing, more and more low spin complexes are getting changed to the high spin one, and we are ending up close to the room temperature with all the molecules transformed from the low spin form to the high spin form. So, this spin crossover phenomenon is very sensitive, where we see that in case of IR we have to go for the corresponding sample preparation. So, FTIR spectroscopy is particularly useful when the sample can support the corresponding powdering or the mulling or the grinding with KBR, because here in FTIR we take the powder sample mixed with some specific amount of potassium bromide powder and we mix it in mortar and pestle, and then we go for the corresponding press and we make a disc shaped KBR pellet. So, this KBR pellet is formed, and this particular pellet is basically being inserted to the machine to record the corresponding FTIR spectrum. So, our sample for knowing these things, that means the grinding with KBR powder and then corresponding pressing it in the corresponding hand press. So, it is within the press. So, we go for pressing this particular material and such that we get a nice KBR pellet, and this KBR pellet is then inserted in the machine. So, if our sample is not robust or not very much strong to support this particular processes for recording FTIR spectrum, is not suited for measuring the corresponding spin transition and the spin crossover phenomenon. As a result, we use only the Raman spectroscopy, because in this spectroscopy there is no need for making this KBR pellet, because it is a very sensitive one with respect to that. So, the spin crossover phenomenon is very sensitive to grinding, milling and pressure. So, we grind it with KBR during FTIR measurement, then we go for the milling and the pressure. So, during these processes our compound might change from one particular spin state to the other, but the advantage of the Raman spectroscopy is that such sample preparation is not required what we use for FTIR sample preparation. So, whatever sample we have for the measurement does not require further preparation like grinding, milling and pressurization in the press to get the corresponding KBR pellet. So, the Raman spectroscopy is a very safe one to measure the corresponding frequencies for SCO complexes, but some of the highly colored samples may affect the measurements because the colored samples cannot be handled nicely in this particular spectroscopy. So, what we see that the same thiocyanate compound, 2 phenanthroline and 2 thiocyanate is there in the cis position, 2 thiocyanate groups are present, and we can have the corresponding stretching frequencies. The figure is not very much clear, but what we see that we are basically going for some of these frequencies, some of these stretching frequencies for this bond, basically iron nitrogen from thiocyanate and within the thiocyanate also, because what we have seen here for carbon monoxide, this is also true for NCS. So, when NCS, the thiocyanate anion is binding towards iron, we can have the corresponding stretching frequencies for C double bond or triple bond N as well as stretching frequency for CS. So, these are the two characteristic stretching frequencies present. If we can monitor these two nicely in the parent salt, that means it can be potassium thiocyanate or ammonium thiocyanate. So, for these two values are known when it is not bound to iron center, but when it is bound to iron center, we can compare these stretching frequencies, that means this Cn stretching frequency as well as Cs stretching frequencies will change due to coordination, and how much it is changing, that will again depend on whether we have a low spin compound or a high spin compound. So, for low spin compound where thiocyanates are bound to the iron site, we have the corresponding or rather characteristic stretching frequencies for this particular spin state. Similarly, the other values what we are getting for the HS complex will also be characteristic for the high spin compound. So, what we are taking? We are taking the Raman spectrum at 100 K and at 300 K. So, at 100 K the corresponding signatures what we are getting over there, particularly this particular value at 2114 due to the corresponding Cn stretching frequency of the thiocyanate, which is characteristic for the low spin compound, and that value signifies that at 100 Kelvin we have the compound exclusively in the low spin state. That means the LS form can be generated at 100 Kelvin, and as we go up, and we have seen that around 185 Kelvin the spin transition is taking place from the low spin to the high spin, and there basically we get this corresponding signatures for the high spin signals. So, high spin signals do appear because the number of electrons occupying the different d levels are different. In case of this particular iron center also. So, as we move for the high spin, so Eg level are getting occupied. So, the interaction with that Eg electron to that of our NCS ligands are different, and the stretching frequency, that means the electron is being pushed some of the electronic charge is being pushed to the orbitals of the thiocyanate groups, and those electron push basically can modify the corresponding staging frequencies of these thiocyanate groups, and this particular staging frequency is going downward from 2134 to 2070. So, that downward movement of this particular staging frequency signifies that we have a high spin situation for this particular molecule. So, whatever high spin iron 2 complex we can have high spin and low spin state, and a shift from 2114 centimeter inverse, this is 2114 to 2070 centimeter inverse, the upper one, the red one, corresponds to the changes in the stretching vibrational modes of the thiocyanate ligand from a low spin state to a high spin state respectively. So, that gives us the clear indication that as we move from a high spin situation to a low spin situation, the corresponding iron thiocyanate staging frequencies, or rather the corresponding Cn and Cs combined staging frequencies are changing, and this is very much characteristic for the Cn staging frequency within the thiocyanate group, and is changing from 2114 centimeter inverse to 2070 centimeters at the lower value for the movement from a low spin to a high spin state. So, like magnetic moment, like Mossbauer spectroscopy, Raman spectroscopy also supporting, and Raman spectroscopy is also very much significant in identifying the corresponding spin state change from the low spin to a high spin situation. Similarly, the other one, though this particular technique requires the corresponding machining, molding and grinding, but FTIR technique is also useful like Raman, because Raman, what we have told you, that is a complementary technique. So, this can also monitor the corresponding transition from high spin to low spin or the vice versa. So, if we have a well connected tetranuclear system where 4 iron centers are present, these at 4 corners is a tetranuclear species, and in this tetranuclear species some bridging groups are present. So, this is basically the bridging unit. So, we have 4 bridging units. So, it is basically a rectangular shaped molecule, and that rectangular shaped molecule, this particular iron center is bridged by this group and is also bridged by other group. So, how we get these things, because this is a very simple practice where we have iron thiocyanate groups. If we can go from iron thiocyanate to some iron azide function, azide is nitrogen triple bonded system which can reach the second iron center. Similarly, on the other axis, if we can have the second iron, and on the other corner we have the fourth iron. So, this will also be connected by another azide group. So, this N3 unit is known as the corresponding azido bridge. So, when we have this particular connectivity for a Fe4 complex, we can have other free positions. So, 4 other free positions we can have, and there we just basically place the monodentate ligands. So, all different monodentate ligands can be placed over there. So, giving rise to a very nice Fe4 complex. So, that is the situation over here, and if we measure and if we monitor the corresponding signal corresponding to the high spin and low spin compound, and there will be change from a high spin to a low spin situation. So, here the cyanide groups are attached to this particular iron side. So, Cn can be monitored this particular from the thiocyanate groups. So, this Cn stretching vibration of FeBTRs is another ligand set, but of similar type what we have seen for orthophenanthroline, and water is the water of crystallization at different temperatures in the cooling mode and the heating mode. So, as we go for cooling and we come back again through the heating mode, basically give rise to the corresponding change in the Fen and the corresponding Cn stretching bands, which is shifting from the change from one spin state to the other spin state. So, the high spin state, the Cn stretching band as 2054 is predominant at higher temperature. So, just now we have seen that how we monitored as the temperature variation, here also the heating mode and the cooling mode can be monitored for monitoring the corresponding stretching frequency for the high spin state as well as for the low spin state. Thank you very much.